Hello, it's Keith here, and today we're going to be starting a new series. We're going to be looking at the ARM processor. Now, the ARM processor started with the ARM2, the Acorn Archimedes, and it's progressed over the years and now basically runs all the mobile phones we use, and it's starting to make sort of headroads into the server industry and things. So ARM has become a very significant player in the CPU industry and is basically the number 2 behind the x86, which I'm covering in the 8086 series. So we're going to be looking at ARM, and we're going to be learning about the basics of how its instruction set works. We're going to be primarily focusing on the ARM2 with RiscOS, but we're also going to look a little bit at the Gameboy Advance, which of course was also ARM based. So we're going to be looking at a few of the simple commands, and we're going to learn how to write some simple ARM programs and look at the instruction set. So let's begin today then. So the first thing we need to understand is that the ARM processor is referred to as a RISC processor, which is a reduced instruction set processor. This means that the instruction design is more simplified, the bytecode is sort of more rigid, and it works a little bit differently, but it's not something that's particularly too scary. There are some things that are quite different to processors we've looked at in the past, like the 68000, but it's not things that are going to terrify us beyond belief. It's just things that maybe work a little bit differently with regards to the way the calls work, and maybe things that we could do in one command before we could do in two. But that said, the ARM does now possess some very, very powerful commands that are really quite remarkable, that a system like RISC-V don't have. So as I say, it's a very impressive system, and it's certainly one that deserves our attention. Now, the ARM processor has a total of 15 general purpose registers that we can use. It does have some others that are system registers, but we're just going to stick to the basic stuff. Now, some of these are used by the system. So number 15 is the program counter. That's the current running instruction, so we don't want to use that. Number 14 is what's known as the link register. Now, when we do a call, now that's like a go sub if you're familiar with BASIC, rather than on other processors, things getting pushed onto the stack, with the ARM, the return address is put into the link register. Now, if you don't understand that, please don't worry about it. I'm just going through the basics of the registers. The important thing is that has a special purpose we'll see later. Number 13 is the stack pointer, but we can just refer to that as SP. Now, 11 and 12 also have some special uses in certain cases, but essentially everything from register 0 to register 10 we can use for whatever we want. We can just use them in any way we like. Of course, there's some flags, and all of this we're going to cover later. This is just a very quick introduction to the processor, just so you have some grounding for when we actually start looking at things. So anyway, let's go over to our code and let's start seeing some programs in action, just some very simple ones. Okay, so I've got a few little programs here. The main one we're going to start with is this minimal example here. Now, as always with my tutorials, I've got a bit of a header here and a bit of a footer, and these are going to allow us to set up for working on either RiscOS or on the Game Boy Advance. And so this is a test environment for us. So if we're playing with a few commands and we want to see some quick results, we can use this code here. So let's fire up our emulator and see this running first on RiscOS. Okay, so here's our emulator running. We're using RPCemu here. You can download the package for this from my website. Now, what we've got here is a dump of all the registers, and that's this monitor command here. Now, BL stands for branch and link. Now, this is the equivalent of a call within the ARM CPU. What this means is it's branch, which means jump to a label, and link, which means transfer the program counter to the link register. Now, if I just switch back to the last screen for a second. Now, you may remember I said before the program counter was register 15 and the link register is register 14. So what happens is the program counter is copied to the link register when the call occurs. Now, if we just go back to our code screen here, if we look at one of these sample lines here, you'll see this getScreenPos function has at the end a move command, which is moving the link register back to the program counter. And this is actually effectively a return command. A bit strange, I know, and we're going to cover all of this later on. But if you're familiar with the BASIC, this is effectively a go sub to a subroutine, and this is effectively a return command for the ARM CPU. As I say, we will cover all of this later. I'm just giving a very brief introduction here. So branch and link is our go sub or our call command. Monitor is a function that's defined within one of these include files. This is a separate ASM file, which we're not going to go look into today. So this include command with the dot at the start defines a file to be included. This bitmap font and this infinite loop are labels. You can tell that because they're at the far left of the screen with a colon, whereas these other commands are indented by a tab, and that means they're commands. So we've got a couple of branch and links, these calls here, to a few functions within these. And this monitor will show the status of all of the registers. Now we can test this if I just do a move and then I do R1, hash 0x1234 and I execute this. You can now see register 1 has changed to 1234. And if I just exit that and I change it to 66660 here, and you'll notice I've got this 0x at the start, which means hexadecimal. And as I say, we'll look at all this again in just a moment. Well, now you can see register 1 equals 6660, and that just shows that this monitor is working. And this should be quite handy if you're just getting started with programming and you want to test a few commands and be able to see some results on the screen. That's what this is sort of designed for. Now, as well as the RiscOS, we can also run this on the Gameboy Advance. If I just run here, and there we go, you can see the same state. Now the 666 is there. The other registers are different because it's completely different hardware, and it's the contents of the header and the footer that are allowing that to happen. They've got some generic graphics setup routines and things so that we can run our test code on either emulator. And the RiscOS is good for ARM2, the very early iteration, and the Gameboy Advance is a much later version of ARM, and so that's quite handy if we're testing the commands that were added later on. So that's going to be our testing environment, and as I say, this is just a very simple example here that we can use as a template. So that's there for us. Now we're going to be compiling with some build scripts that are provided with this development environment. Now hopefully if you download the tools I've provided here, you can just press F6 and you will get an option here, and it will let you select one of the destinations to build to. We've got Gameboy Advance and RiscOS. Now this RiscOS strong ARM doesn't really work, I don't believe. I was hoping to be able to use some more advanced ARM commands, but it seems there's some problems with that. So we'll just have to stick to Gameboy Advance for the more advanced commands and RiscOS for the ARM2 commands. Okay, so that should easily allow us to build, and the script itself, we're using Vasm to compile. We're specifying a build file. We're specifying the version of ARM we're compiling to, ARM2 in this case. We've got a few options here to set various settings to compile correctly, and we're also defining a few symbols that I use in my code here and there, but that's nothing new. We're outputting a listing file here. This is a debugging tool. It will show the source code and the bytes that compiles to. It's quite handy if you're having trouble or if you suspect your assembler is making changes behind your back. Some of them do optimization, and in some cases in testing things haven't worked the way I expected because the ARM is kind of almost correcting mistakes that I'm intentionally trying to make. So it's sometimes worth seeing that listing file, but it's not something you would need necessarily as a beginner. And then we're outputting a file with an FF8 extension, which is an executable for RiscOS. And you can see here we're copying it to a folder that RPCMU is using as a disk drive. Now hopefully you can download these scripts and just use them as is, but I'd just like to give a brief introduction to Vasm itself that we're compiling to, just to get started with these tutorials. Okay. So today's lesson is just going to be the real basics of this system. We're going to go over some very simple commands with regards to moving data around the registers and a little bit of memory processing, and we're going to see all of the results on screen. We're going to go far deeper into this over later lessons, but the first one is just a starting introduction to show you my tools, to give a brief description of the system, and also just some very simple register manipulation to give you a feel of what kind of things the ARM can do. Okay, so let's begin. Now we're going to start with this move command here. You can see here we're starting at the very beginning of our code with the setup of the screen, and then we're jumping to this set of tests. We're using test reg add and sub here. This is a branch, which means there's no return, and we're branching to the label here, and the label's on the left hand side with a colon. And then tab indented, we've got our first command, mov. Well, you can probably guess that's a move command. It's quite similar to a lot of other systems that have that. Now, on ARM, in general terms, the destination is on the left and the source is on the right. Now sometimes there's multiple registers, and sometimes you can see here that there's 2 commas here and there's 2 registers, and we'll discuss those in just a moment. But in this case we're moving the value here into the register here, and you can tell this is a value because it's got a hash here, so that means it's a value. And you can see there's a 0 followed by an X, and 0x means hexadecimal, so we're loading hexadecimal 1234 into the register here. Now with regards to hexadecimal, this is of course base 16, whereas decimal goes from 1 to 10 with numbers 0 to 9. Base 16 has an extra 6 digits, if you will, A, B, C, D, E and F. Binary just has 2 digits, 0 and 1. Now if you need to have some help with hexadecimal, because you will need to have some understanding of it later on. This lesson you can probably just look at what happens and have some appreciation, but if you're going to start doing serious programming yourself, you'll have to understand hexadecimal and binary to a good extent. Now the easiest thing to do is just get your Windows calculator up. I'm using Windows 7, but the Windows 10 one is actually even better. If I type 1234 here and click decimal, you'll see that's decimal 4660. And if I type 123 in decimal and click hexadecimal, you can see that's hexadecimal 7B. So if you're just getting started, that should help you out a little bit. Now I do have a full tutorial on hexadecimal on my YouTube channel, so please have a look for that, because that goes into a lot of detail with a lot of examples. So if you're looking to learn, that should help you out. But today we can just take it that we're loading 1234 hexadecimal into R0 here. Now all of the registers on the ARM are 32-bit. The value here being 2 bytes is 16-bit. So we're loading 1234 in the low half of the register here, and then we're loading R1 with 1234 in the top half of the 32-bit register here. Okay, well let's just fire that up and let's see the results of that. So you can see here R0 is 1234 here, and R1 is 1234 in the top half of the register. Okay, now here's a very unusual thing. It's very unusual to me anyway. Now let's say we wanted to load a larger number. Let's say we wanted to load the top half with 1, 2, 3, 4, 5. Well, okay, not quite the top half, slightly more than half, but you get what I mean. Well, that looks pretty logical that we would want to do that. Well, let's have a look at what happens. Oh, well, if I just change my window here. Sorry, I'll just size my window here. I apologize for the mobile phone users. It's very small, but I will read it out. It says error, constant 12345 is not suitable for 8-bit rotated immediate. That sounds a bit jargonish. Well, we can make it a bit easier. What it means is we can't set more than 4 digits at a time in hexadecimal in a register with the move command, and this is all relating to the way that the byte code actually compiles. You see, this command here compiles to a single 32-bit chunk of data, and sort of half of that will be the command move and the register number that we're writing to, and the other half is the digits and effectively the position of those digits within the data, within the destination register. Now let's just switch over to my other screen here, and if we scroll around a little bit, effectively the bits are being shifted when they're being stored by the move command in the immediate register. So you can see here there's a kind of shifting effect here, and that's basically what is happening internally. Now you don't need to obviously worry about that kind of thing, but the important thing you do need to understand is that you will be limited to how many bytes you can set at a given time, and in this case we can only change 2 bytes of the value when we're doing a move command. Well, if you're going from 8-bit and 16-bit, you probably think, well, I don't need 32 bits anyway. I mean, maybe you're thinking that. But if you're not, or if you really want those extra bits, you're probably thinking, well, that's going to be pretty weird. How do I cope with that? Well, there's 2 options. We can either move the first half of the value and then add the second half, and we'll look at that later. Or the alternative is we store the value in a piece of memory and then we load in from that piece of memory. And so that's another good option. But we're going to look at all of this later on. It's just a thing that could easily catch you out. And sounds kind of crazy if you're familiar with other systems, that you can't load your whole register in one go on a 32-bit system. It seems like, well, the 16-bit systems can, the 8-bit systems can, why can't the 32-bit systems? And it's like, well, that's kind of part of RISC, and RISC-V is the same. There are limitations in the same way. Now, some assemblers may have special commands that will actually allow us to load the full part, and they will actually do things internally and split the command up automatically for us. And that's where your listing file can be quite handy. But as I say, in this case, I wanted to prove the point that it doesn't work, to show, you know, this is the limitation. And so don't be surprised if you try and do this and it doesn't work. Okay, so we can only load half of the 32-bit register with a move command, but we can load it into the bottom half, the top half, or any middle half. You know, we can, just to make it clear, we can do that just fine. There you go, that worked absolutely fine. There it is, you see. So it's the number of consecutive digits. Okay, so we've learned about the basics of moving a hexadecimal value into a register here. Now, what we're going to do next is we're going to look at some other kinds of value that we can load in, because while in a lot of cases we'll want to work in hexadecimal for at least some testing purposes, there will be times we need to use binary, and there's times we need to use decimal. Now, in VASM, if we want to use hexadecimal, we use 0x, the X marked hexadecimal here. And that's because we always need these to start with a digit. If we started with F0, then the assembler would think that was some kind of label. So they always have to start with 0, and then we have the X next to that to denote hexadecimal. If we're working in binary, we can use 0b. And if we don't specify anything like that, and we just specify a number, then we work in decimal. Now, unfortunately, I don't know if this is just VASM or just me being stupid, but I can't find a way to get VASM to store ASCII characters. Most systems would allow you to put a letter in quotes, and it would compile that and work out the ASCII equivalent. I can't figure out how to get VASM to do that, so I'm having to specify decimals here. So this is the equivalent of a letter A here, and so I'm just storing that as a decimal here. So let's just compile that, and we'll see all of these results here. Okay, so let's have a look at these values here. Well, first we've loaded hexadecimal 1234 into R0, and you can tell that because of the X here, that means hexadecimal. And you can see here that 1234 has been loaded into R0 at the top here, just like you can see here. Now next we loaded binary 10101010 here, and you can tell it's binary because of this B here after the 0. And you can see here R1 contains the value AA, just here. Now let's have a look at our calculator, and if we do if we change to binary, sorry, and we do 10101010, and we change to hex, you can see AA. So there we go, we can see that has loaded in just fine. And R2 contains 41, and we loaded in decimal 65 here, which is the equivalent of an ASCII A. So if we just do, we could enter the hex, but let's enter the decimal 65 and change to hex, and you can see that's hexadecimal 41 here. So you can see here R2 has been loaded correctly. Okay, so we've looked at loading immediate values into registers, and an immediate value means a value that's held in the source code as a number and is in the same line as the command to perform the operation, in this case a move. So we've moved these values into these registers, but the move command can do more than that. It can also transfer one register's value to another. So in this case, we've got a move command. The destination is on the left of the comma again, R0. The source is on the right-hand side, this R2 here. So we're moving R2 into R0 here. And let's just see that on our screen here. So you can see here before, R2 was equal to 41 and R0 is equal to 1234. Well, now we've transferred the 41 here from R2 to the R0, and you can see R0 now also equals 41. And so we've transferred the entire 32 bits here to the 32 bits here. And that's what the move command has done for us. So we've looked at the move command for setting registers, which is a good start. We can use that to load immediate values and also to transfer between registers. But of course we want to be able to do a little bit of mathematics. So we need to look at some more commands. So we're going to look at addition and subtraction. So these again are 32 bits, and we're going to use an immediate value in these examples again. So we're going to be performing an add. Now the add command, you can see, takes 3 registers here. And the way you want to think of this is that the left-hand side again is the destination, and the right-hand 2 are the two parts that are the maths is being performed on. So add R0, R0, all of this lot means add R0 and 0, quadruple 0, 5, 6, 7, 8 and store the result in the left hand side register R0. Well, that means one of the source values and the destination are both R0, but that just works fine. But that's not necessarily what we have to do. We could say R1 equals R0 plus 1. In this case, it's just decimal 1 or hexadecimal 1, they're the same value. So we're effectively adding 1 to R1 here. So we're effectively adding 1 in a rather crude way to R0 here and storing the result in R1 here. So there we go. That's a perfectly acceptable thing to do. We've got other options. We can do a subtract. We can do that in the same way. We've got R0 here, and we are just subtracting this top nibble set to 1 here from R0. And then we're just subtracting 1 from R1 here again, and we're storing the value in R1 this time. So this time we were using register 0 as the source and register 1 as the destination, but in these cases we're using the same register itself, and both are perfectly legitimate. And that's one of the powerful things about ARM. In most instruction sets we've looked at in the past, you would have a destination, and the destination of the add or subtract command would also be one of the sources, whereas in this case we can add register 2 to register 3 and store the result in register 0, and register 2 and 3 are unchanged. So that gives us quite a lot of flexibility there. So if we just compile this and have a look. So let's see each stage as we went along. So first we loaded the top 16 bits as 1, 2, 3, 4 here. You can see that just here. And then we added 5, 6, 7, 8 to the bottom part here. And now you should see how we can sort out that problem of not being able to load the full 32 bits in one go. What we can do is we can load in the first half and then add the second half, and you can see we've now set that value that we want, and you'll see that a few times in my test code. I do that quite a bit. So that's what we can do there. And then what we've done here is we've set R1 to R0 plus 1, and you can see here this was 1, 2, 3, 4, 5, 6, 7, 8, and this is 1, 2, 3, 4, 5, 6, 7, 9. We have indeed added 1, and of course we have left R0 unchanged by that operation because the destination, the left hand side, was R1. Okay. Now, addition isn't the only thing we can do, as we said, subtraction. In this case, what we've done is we've subtracted the top nibble of 1 from R0. Well, if you look before, it was 1, 2, 3, 4, 5, 6, 7, 8. The 1 has been subtracted, so now it's 0, 2, 3, 4, 5, 6, 7, 8. So there we go. It's a strange thing to do, but that's what we did. And then we subtracted the 1 that we added before to R1. And so you can see that R1 is now 1, 2, 3, 4, 5, 6, 7, 8 again, which it was when it was loaded in from R0 by this addition command up here. So we've got some options there with various values here. Now I'm showing these with immediates, but we don't have to use immediates here. We could use a register. We could subtract R0 from R1 and store the result in R1 here. And so there you go. You can see we've subtracted R0 from R1, and that has given us this 1, lots of zeros and then a 1 here. So I'm showing these with immediate options here, but there's a wide variety of choices with regards to the register that you can use as the right hand side parameter. Now what I'd suggest you do is you download my cheat sheet, which has got some more details on this, and also if you have a go yourself, and you should be able to start to understand what the limitations are. Basically the parameter here always has to be a register. The parameter on the right hand side can be more complex in a lot of cases. We're going to go over in next week's lesson over the all of the addressing modes, the different options that we can specify here, the registers, the immediate values and so on. It's going to be quite complex, but we will go over that, so please follow along for that. So there we've had a look at some simple addition, subtraction and setting of registers. Okay, so let's have a look at reading and writing from memory. Now we've looked at using the registers, but of course we're going to need more storage than that because we've only got about 10 registers that we can reasonably use, and you know we're going to need to store things to and from memory, and we're going to start looking at that now. Now with the ARM processor, there's sort of two ways we can work with memory. In limited cases we will be able to use the immediate values if the memory we're working with is nearby, but in the same ways we can't load very long strings of hexadecimal into an address, we also can only address relatively nearby pieces of memory with directly without using another register to store that address into. So what we're going to do here is we're going to load in from the nearby address test val here, and we're going to load with this LDR command into R0. So R0 is the destination and test val is the source address here. And then we're going to show the results to the screen. We're then going to add 1 to the register R0, which we read in from test val. And then we're going to use str, which is store, and this is one of the real exceptions, because on this case the left hand part, the register R0, is the source and test val, the address, is the destination. So this is storing R0 to address test val, and then we're going to show the monitor again so we can see what happened, and then we're going to show the address here again to the screen, and we're going to see the results there so that we can confirm that that change occurred. So let's fire that up and see that happening. So let's fire up our code here. And here it is. So you can see here we loaded the test value with FEDCBA98 here, and our show test RAM function shows that to the screen. So here it is here, but you can see that it's backwards. Now that's probably not much of a surprise to you if you've done assembly before. This is something known as little endian, where the lowest byte values come first and the highest byte value comes last. So 98BADCFE here is this just reversed because that's the way we store things in memory. Now with the ARM processor, that's sort of optional. In theory the processor can work in either mode, but in practice I believe it's basically always little endian. So that's what we will be working with. So we showed that value to the screen here. We then loaded in from the address test val into R0 with the LDR command here. And you can see that just here. We've loaded that value in. We then added 1 to R0 and we stored the result in R0 because the result is stored in the left hand side register with add. And so you can see that went up to 99 here. And then we stored that value, and of course that didn't change there. But then we dumped the memory to the screen again, the same memory as we dumped here, which is of course this value here. And you can see that has now gone up to 99. So we successfully changed our register value here, and after loading it in here we stored it back here and changed the memory accordingly. Okay, now one thing I do have to point out is if we run this on the Gameboy Advance, it will run, but you can see here the test value started off as 98 here and it ended as 98 here, and the reason for that is that this is running from ROM and this is read-only memory of course, so that write command didn't work. So we will have to really test this on the RiscOS machine, but as I say, we can work with the RAM within the Game Boy Advance in other examples, but for this very simple example it didn't really feel appropriate to do that, so we're just testing on with nearby memory here. Okay, now that's how we can use an address specifying it in line, but there is another alternative. What we can do is we can load the address into a register and then use that register as the source, and we put it in little square brackets here. Now we'll be going over all of these options next week in the addressing modes tutorial, where we'll be going through each addressing mode possibility in a simple example. But just for today I thought we'd go over the basics of them just here. So what we're doing here is we're loading in R1 and we're loading it from the address in R2, and you can see that's denoted by these square brackets here. And then we're going to show R1 to the screen. Okay, so let's have a look at that. Well, you can see that this memory address here is 8608 just here, and we loaded that into R2 with the ADR command. The source was test val and the destination was R2, and that's why you can see here R2 is 8608. There we go. So we then loaded in R1 from R2, and you can see R1 is FEDCBA99, which is the value that this currently holds. Then what we've done here is we've loaded a new value in from an immediate 00122100, and we've loaded a different address. Now this address is being specified differently. It's specified with a hash, and that's because we've defined this with a symbol. Now we'll have a look at that in just a moment. And then we've stored R0 to the address in R2 with those square brackets again. Now what we've done next is we've shown this other RAM area, and this RAM area on this system is 8000. You can see 001221 and then 00 with little endian of the value we've stored here. Now this user RAM it's a different location depending on the system. So if I just have a look at my source Gameboy Advance header, you can see the user RAM is being defined as being equivalent to this long address here, which I'm not going to try and read out. So this is known as a symbol. Now a label, when we define it, is defining it, it's pointing to a byte within the compiled source code, and the jump will jump to that byte. But we can also define other kinds of symbol, and this is saying, well, when you see user RAM in this source code, it equals that value. But with VASM, that does mean that we can't use the load address command to actually read this in. So rather than using ADR as we did here, with VASM we have to specify user RAM with a hash symbol because it's actually a numeric value. But effectively, the result will be fine for us. R2 will contain the address we want to use, and then the store command will store R0, because remember that with the store command especially, the left hand side is the source and the right hand side is the destination, and the destination is the address in R2, and the address in part is defined by these square brackets here. Then we're showing the results to the screen, and we're showing the user RAM area to the screen. We've just got these little user RAM functions and test RAM functions just to show bits of memory to the screen easily. And we're not going to go into the exact workings of those. These are just little functions that you can see further down in the source code. They're using some little tools I've written just for these tutorials, but it's way beyond what we're trying to do in this lesson. We're just looking at the real basics of the system. We are going to be doing more of that later in the next episode, which is going to be the addressing modes, where we go over each addressing mode in some detail. But next we're going to have a look at this second read and write example. So let's go and have a look at that. And here it is just here. Now we've looked there at loading and storing to memory, but we've been working in 32 bits because that is the way the ARM CPU wants to work, if you will. That's the way it's most efficient. But obviously there's going to be times where that's not appropriate. For example, my graphical font I use is 1 bit per pixel and each character is 1 byte wide. So loading in 32 bits isn't going to make a lot of sense. So there will be times where we need to work in bytes, and the ARM2 allows us to do that. We just add a B letter to the end of our load or our store commands, and instead of loading 32 bits, it will load in just 8. Now you can see here we're loading in a full set of ones here. You'll go quadruple F and then adding quadruple F, making all of the bits of the register 1, and that's just so we can see what happens when we load in some test values. So let's fire this up and let's see the example here. And you can see here we loaded R0 with all ones here, which sets it all to Fs. Then we loaded in from test val as before, and we loaded in just a byte LDRB into R0. So we're loading in from this address here, the left hand side, little endian, and we loaded in 98. But notice how all of the other bits have been set to 0 here. So you can see here that it's actually cleared out the rest of the register, which is quite kind of it in some ways. Because that was probably going to solve us some problems. But anyway, we've loaded in the value here, and then what we've done is we've added 255. Now, of course, the limit of a byte is 255, so that's going to make it roll over and go beyond a single byte. And this was just to make the point that when we stored the byte back and showed to the screen again, well, the 98 plus 255 in hexadecimal was 197, but when we stored the byte back, we only stored the byte back, so only 97 was stored here, and that this one was lost. Now, of course, if we took the B off, we will actually just do that. So if we take the B off and if we compile again, well, lo and behold, now all of these bits have been set to 0 and our 1 has been stored just here. So that's what we can do there. Now you may be thinking, well, that's how we can do bytes and that's how we can do 32 bits, but what about if we want to do 16 bits? Now, we will be looking at that in a later lesson, but unfortunately the original ARM2 didn't support those operations, so we do have to either work in 8 bits or 32-bit on the ARM2. So that's the kind of limitation there. Now, another thing we just will briefly cover is we can store data inline in our code here if we need to, but we do have to make sure we're always 32-bit aligned when it comes to the program code itself. So you will put in an align for command if there's any possibility you won't be aligned correctly in your code here. So for safety, I probably should have put an align for in just here. Now, of course, this is 32-bit aligned, but just in case I decided to put a byte in afterwards, if I put byte 1 in here and then compiled, that will work just fine. But if I take this out, I will get it. I've actually got a warning saying it's been auto-aligned, which is better than nothing. But that was sloppy coding of me. That's a thing you shouldn't do. Now the ARM literally cannot run commands unless they're correctly aligned. And in the original ARM processor, the ARM2, the bottom 2 bits of the program counter actually had a completely different purpose. They were used for statuses for the processor mode, I think it was. But anyway, that's basically what we're going to cover today. So let's go back to our example code here. Okay, so we've covered everything that we needed to there. We've really just done the basics, seeing a few ARM commands and getting a feel for the absolute fundamentals of the system. It is a little bit more tricky than some of the systems. If you're familiar with 68,000 and things, I personally find it a bit harder. But you have to admit the power of it, and we really haven't looked at that power yet. We will start to see it when we look at the addressing modes, because it can do some crazy stuff compared to other systems. So we'll have a look at ARM more next time. I hope you've enjoyed this. I hope you found it interesting. If you have, please like and subscribe. If you haven't, then I guess don't. But I do have other tutorials. If you want to see other content, I've got 8086 tutorials, 6502 and 68,000. I'm also going to be doing RiscV very shortly as well. So if that sounds something you would be interested in hearing a bit about, please follow on for that. Anyway, I hope you found this interesting today. You can download all the source code for today's example from my website, and the development tools, the build scripts and the pre-configured Notepad++ will be available for download. So hopefully that will help you get started a bit quicker if you're looking to do some programming. Anyway, whatever, I hope you've enjoyed this. I hope you found it amusing. Thanks for watching today, and goodbye.